Welcome to this video on magnetic hysteresis and the BH curve. We will explore the dynamics of magnetization in ferromagnetic materials, like the example shown here for silicon steel. The BH curve helps us understand key magnetic properties. Saturation is when the maximum magnetic flux density is reached. Retentivity is the residual magnetism, and coercivity is the reverse field needed to demagnetize the material. The area of the loop represents hysteresis loss, which is energy dissipated as heat. Let's test your knowledge with some practice questions. First, what does B represent in the BH curve? It's flux density, the total magnetic lines of force through a unit area. Next, H represents field intensity, the external magnetic field applied. Finally, the area enclosed by the loop is the hysteresis energy loss. Question 4. Magnetic flux density. B remaining when H is reduced to 0 is retentivity or remanence. Question 5. The reverse magnetizing force H, required to reduce residual B to 0, is coercivity. Question 6. Soft magnetic materials, like soft iron, are characterized by a narrow BH loop, indicating low loss. We repeat the practice questions for reinforcement. Retentivity is the magnetic flux density remaining when H is 0. Coercivity is the reverse magnetizing force needed to remove residual magnetism. Soft magnetic materials have a narrow BH loop, resulting in less hysteresis loss. Materials with a broad hysteresis loop are used for permanent magnets, as they require a strong field to demagnetize. The SI unit for magnetic field intensity H is ampere per meter, and the SI unit for magnetic flux density B is Tesla, or Webers per square meter. The phenomenon where magnetic flux density B lags behind H is called magnetic hysteresis. At magnetic saturation, increases in H produce no further increase in B. The ratio of B to H defines the material's magnetic permeability, which indicates the ease of magnetic force passage. To minimize hysteresis loss in a transformer core, use silicon steel, a soft magnetic material with a very narrow loop. For non-magnetic materials, the BH relationship is a straight line passing through the origin. The curve is non-linear for ferromagnetic materials due to the random stepwise alignment of magnetic domains. The primary objective of the BH curve experiment is to trace the loop and determine key magnetic properties. A cathode ray oscilloscope, or CRO, is commonly used to display the hysteresis loop in real time. In the CRO setup, the X input represents magnetic field intensity H, and the Y input represents magnetic flux density B. The toroidal shape of the specimen minimizes magnetic flux leakage, ensuring accurate measurements. The RC integrating circuit converts the secondary coil's induced EMF into a voltage proportional to B for the CRO. An AC power supply is necessary to continuously reverse the field, completing the repetitive magnetization cycles needed to display a stable loop. To calculate hysteresis energy loss, determine the area enclosed by the BH loop on the CRO. Magnetic saturation is indicated when the top and bottom tips of the loop flatten horizontally. Retentivity is measured at the y-intercepts, representing the residual B when H is 0. Coercivity is measured at the x-intercepts, which is the reverse field required to zero the residual flux density. Replacing a soft core with a hard core results in a broader, wider loop with higher hysteresis loss. To demagnetize a specimen, apply AC and slowly reduce its amplitude to 0. Here are the important formulae related to the BH curve. H is magnetic field intensity, B is magnetic flux density, mu is magnetic permeability, and chi is magnetic susceptibility. Hysteresis energy loss, W, is related to the area of the BH loop and is often described by Steinmetz's law. Thank you for watching this video on the BH curve. We hope this session was insightful and helpful in understanding magnetic hysteresis.